Hi everyone, thanks so much for coming to this video. We're going to be learning about intermolecular forces today, so these are the learning objectives. The first is to understand about the three different types of forces, and then we're going to look at the interactions in molecules such as water, and then we're going to understand the results from hydrogen bonding for water, so why it has a high melting temperature and boiling temperature, and the density of ice compared to water. And we'll also learn how to be able to predict the presence of hydrogen bonding in molecules, to understand physical properties shown by materials, and to understand factors that influence the choice of solvents. So there's three types of intermolecular forces that we need to know about. The first one is van der Waals, and this is the weakest type of intermolecular force, and this is because temporary induced dipole-dipole attraction is created due to uneven electron distribution. And this is because of the movement of electrons. This occurs even in molecules with no polar bonds. So this is actually present in all simple molecules. So all covalently bonded structures which are simple molecular. And the rule is the bigger the molecule, the more electrons it has, so the greater the van der Waals forces. So, for example, if we had chlorine, so we already have a chlorine here, and the electrons are spaced evenly because there's no difference in electronegativity because it's not a polar bond. If we then approach another Cl-Cl bond, which has even distribution electrons again, so what would happen is that when it approaches, we have this Cl-Cl here, and another Cl-Cl here. These electrons over here get repulsed. So more electrons gather around the chlorine which is further away. So then this chlorine becomes delta negative and this becomes delta positive. And because of that, more electrons gather around this chlorine because this is delta positive. So then most of the electrons are attracted to it. So then they do this. So more electrons are attracted to this delta positive, so less are attracted to this chlorine. So what happens is that this then becomes a delta positive and this one becomes a delta negative. The second intermolecular force is a permanent dipole-dipole attraction, and this is found in molecules with polar bonds because they have an overall dipole. A dipole is just a difference in the electronegativity, basically, and there are attractions between these permanent dipoles in neighboring molecules. So, for example, if we had hydrogen chloride, and then we had another hydrogen chloride. Chlorine is a lot more electronegative than hydrogen, so that would get the partially negative charge, and the hydrogen would be partially positive. Same with this one. And so there would be a permanent dipole attraction between them because a partially negative charge will be attracted to a partially positive charge. And if they're not arranged in this way, they normally rotate in order to be attracted like this. So the third intermolecular force you need to know is hydrogen bonding, and this only occurs when a hydrogen atom is bonded to a very electronegative atom. So normally only fluorine, oxygen, or nitrogen. The electronegative atom needs to have a lone pair available to bond with the hydrogen atom of another, and the polar bond leaves the hydrogen nucleus exposed, and so there is a strong attraction from the lone pair on the fluorine, oxygen, or nitrogen of one molecule to the exposed hydrogen nucleus of another molecule. And if we have a look at water, for example, water looks like this. And there's two lone pairs. The oxygen will be the partially negative, and these two will be partially positives. And then these will actually form bonds with the hydrogen of another water because this is a lone pair. So this forms with water, another water, and then it happens again because the oxygen will always be partially negative and the hydrogens will always be partially positive. So they'll always be attracted to the oxygens of another water molecule. And one thing to note is that this angle here has to be 180 degrees. So a straight line. So the importance of hydrogen bonding, for example, the molecules in ice are slightly less packed than in liquid water, so they form on top of ponds, and this insulates the ponds, so it basically keeps the fish alive. So that's quite a good feature for it to have. What happens when ice forms water is that the hydrogen bonds break. So hydrogen bonds are actually the strongest out of the three intermolecular forces, but it's a lot weaker than covalent bonds. So they don't take very much energy to overcome, really. So they can break to form water, but they can be really easily reformed to form ice. And the reason why I drew the waters to be 180 degrees is that a rule for hydrogen bonding is that always when something hydrogen bonds, the angle will always be 180 degrees. This is just a general rule, but simple molecules have low melting and boiling points, and giant covalent structures have high melting and boiling points. And this is because with simple molecules, we're trying to break the weaker van der Waals forces or whatever intermolecular forces there are in between the molecules, compared to in a giant covalent structure when we're trying to break the strong covalent bonds between the atoms, and that takes a lot more energy to overcome, hence why it has a higher melting and boiling point. Now we're going to talk about hydrogen bonding in water in more depth. So there's two features of water that are caused by hydrogen bonding, and the first being that ice is less dense than water, and the second is that water has a relatively high melting and boiling point. So firstly, ice is an open lattice with hydrogen bonds which holds the water molecules apart, and so when it melts, the rigid hydrogen bonds collapse, and this allows the water molecules to move closer together. The distance the molecules are held apart is what makes ice less dense than water, because water molecules are so much more closer together. And secondly, hydrogen bonds are much stronger than van der Waals forces, because hydrogen bonds are the strongest out of the three intermolecular forces. And so this means that more energy is needed to break these hydrogen bonds, so they have a higher melting and boiling point compared to different molecules, even though water is also a molecule. Now we're going to look at the effects of properties of intermolecular forces. So we've learned about the intermolecular forces and how they're quite weak, the weakest being van der Waals and the strongest being hydrogen bonding. So now we're going to see what that kind of affects. So the first is the trends in boiling temperatures of alkanes with increasing chain length. Now, alkanes are organic molecules that we'll learn about later, but alkanes are basically made up of carbon-hydrogen bonds. So, for example, we have methane, which is CH4. So it only has carbon-hydrogen bonds. So as the length of the alkane chain increases, the boiling point increases. And this is because there are more points of contact with each adjacent molecule. So each molecule next to it, there are more points of contact because it's bigger. So that means there are stronger induced dipole-dipole forces between adjacent molecules. So basically there's more van der Waals forces, so the boiling point increases because more energy is needed to overcome them. Secondly, the effect of branching in the carbon chain on the boiling temperatures of alkanes. So we have an alkane here. An example of a branched alkane would look like this. So this would be the branch of this alkane. And a straight chain alkane will have a boiling point higher than a branched chain alkane. And this is because of the greater surface area in contact with other molecules, because branching makes molecules more compact, and this reduces the surface area. So basically this branch here is quite compact with the main chain compared to if it was just 4 carbons in a straight chain with the hydrogens. This has greater surface area, so therefore the boiling point is higher because it has more of the forces to break, whereas because this is a reduced surface area, the boiling temperature will be less. Number 3 is the relatively low volatility of alcohols compared to alkanes with a similar number of electrons. So alcohols have an OH bond. So, for example, you could have methanol that looks like this. This is an example of an alcohol. And the reason why alcohols have a higher boiling point than alkanes is because the intermolecular forces of alcohols are hydrogen bonds, unlike alkanes with van der Waals forces as their intermolecular forces. So we have van der Waals still here with the CHs, but then we have hydrogen bonding here. And hydrogen bonding is the strongest of the intermolecular forces, so therefore the boiling point is higher compared to if we just had the normal alkane. And now we're going to look at the trends in boiling temperatures of the hydrogen halide. So this is when we react hydrogen with a halogen, so group 7. So the general increase in boiling point from H2S to H2T, H2S is here, and H2T here. So there's a general increase, and this is caused by increasing London forces. So that's another word for van der Waals. So there's more van der Waals forces between the molecules because there's more electrons. So that means that the boiling point increases. And then the anomalously high boiling points of water, ammonia, and hydrogen fluoride are caused by hydrogen bonding because we have OH bonds here. We have NH bonds here. And we've got a HF bond. And we know that hydrogen bonding is the strongest of all the intermolecular forces. So that must be why these 3 have such high boiling points compared to all of these down here. And they also have van der Waals forces because everything has van der Waals forces. So this means that more energy is required to break the hydrogen bonding and the van der Waals forces, and so they have higher boiling points. So now we need to look at choosing solvents. So the first one is water to dissolve ionic compounds in terms of the hydration of the ions. So when an ionic lattice dissolves in water, it involves breaking up the bonds in the lattice and forming new bonds between the metal ions and the water molecules. So the negative ions are attracted to the partially positive hydrogens on the polar water molecules, because a water molecule looks like this. So there's covalent bonds between the oxygen and the hydrogen, but this has 2 lone pairs of electrons free to bond with other molecules. And because oxygen is so much more electronegative than hydrogen, the bonds are polar, and we have that oxygen becomes the partially negative charge and the hydrogens are the partially positive. So this is saying that the negative ions of the ionic lattice are attracted to these hydrogens on the polar water molecules. And then the positive ions in the ionic lattice are attracted to the partially negative charge of the oxygen. And so the higher the charge density, the greater the hydration enthalpy. So the hydration enthalpy is how well it absorbs the water, so basically bonds with the water. And charge density is basically how much charge it has in a small amount of space. So smaller ions or ions with larger charges, as the ions attract the water molecules more strongly. So number 2, to water to dissolve simple alcohols in terms of hydrogen bonding. So smaller alcohols are soluble in water, and that's because they form hydrogen bonds with the water, because alcohols have that OH group. So they can form hydrogen bonds with the water that looks like this. And the rule is that the longer the hydrocarbon chain, the less soluble the alcohol. Number 3 is water as a poor solvent for compounds. And this is in terms of inability to form hydrogen bonds. So the solubility of haloalkanes in water, haloalkanes aren't very soluble in water because they can't form hydrogen bonds. A haloalkane is like a normal alkane, but it has a halogen attached, so instead of a hydrogen. So, for example, we could have this molecule here. So there are CH bonds, but one of them is replaced by a carbon halide bond. So this is a haloalkane, and they aren't very soluble in water because they cannot form hydrogen bonds. And the energy required to break hydrogen bonds in water is higher than the energy released when new bonds between the haloalkane and water are formed. So in conclusion, non-polar compounds do not dissolve in water, and the attractive forces that operate between the particles in a non-polar compound are weak dispersion forces. However, the non-polar molecules are more attracted to themselves than they are to the polar water molecules, and so that's why they don't form bonds with the water. Number 4 is non-aqueous solvents for compounds that have similar intermolecular forces to those in the solvent. Compounds which have similar intermolecular forces to those in the solvent will generally dissolve. And non-polar solutes will dissolve in non-polar solvents. So, for example, iodine, which has only van der Waals forces between its molecules, will dissolve in a non-polar solvent such as hexane, which also only has intermolecular forces. So non-polar solutes will not be dissolvable in polar solvents, such as water, but it can be dissolved in non-polar solvents. So now we're going to move on to some questions. The first question asks to place the following elements in order of strength of the van der Waals forces between the atoms, weakest first. So we learned before that if you have bigger atoms, that means more electrons. So strength of van der Waals increases. And so basically we just need to place them in order of size. So we have argon, which is in group 0, helium, which is also in group 0, krypton, which is in group 0, and neon is also in group 0. So that doesn't help us, so we look at the periods. So argon is in period 3, helium is in period 1, krypton is in period 4, and neon is in period 2. And so now this helps us a lot because we know that helium has 1 outer shell, and we know that argon has 3 outer shells. 3 shells, sorry. So we can tell that krypton is the biggest atom because it has 4 shells. And so the order of the elements in strength of van der Waals forces would be helium, neon, argon, and then krypton. So this would be getting stronger. For number 2, draw 2 hydrogen bromide molecules to show how they would be attracted together by dipole-dipole forces. So if we draw 1 hydrogen bromide, we can see that bromine is in group 7 of the periodic table, so it's a lot more electronegative than hydrogen. So we give that the partially negative charge and hydrogen partially positive charge. And so if we had another hydrogen bromide molecule here, which had the same thing, then this partially positive charge would be attracted to this partially positive charge. And so we would get a permanent dipole-dipole attraction between these 2 hydrogen bromide molecules. And what I was saying before was that if, for example, we had hydrogen bromide like this, but one of the hydrogen bromides was like this, and these were delta negative, delta positive, then this one would rotate in order to make this configuration so that they would be attracted to each other. Hi everyone, thanks so much for joining this video. We're going to look at some harder questions for the topic of intermolecular forces. So the first question is telling me to draw a dot and cross diagram for a molecule of water, to state how many lone pairs it has, and to explain why water molecules form on average 2 hydrogen bonds per molecule, whereas the ammonia molecule forms only 1. So starting with the dot and cross diagram for a molecule of water, we have 2 hydrogen atoms and 1 oxygen atom. And so the hydrogens each share an electron with the oxygen. And so the oxygen shares an electron back. So they're 2 covalent bonds. And because oxygen is in group 6, that means it has 4 electrons which are left unbonded. And this is the dot and cross. And so for A, state how many lone pairs it has. That means it has 2 lone pairs. It has this one and this one. So these are lone pairs. And so it has 2 lone pairs. For B, explain why water molecules form on average 2 hydrogen bonds per molecule, whereas the ammonia molecule forms only 1. So if we have a look at ammonia, we have nitrogen, which is in group 5. So it has 5 electrons. If we bond 3 hydrogens, and these are all covalent bonds, then we have only 1 lone pair left, this one. And for hydrogen bonds to occur, we have to have a hydrogen and a very electronegative element, such as oxygen, fluorine, or nitrogen. So in both of these cases, they can both form hydrogen bonds. But with water, water has 2 lone pairs. So on average, it can form 2 hydrogen bonds because this one here can form a hydrogen bond with a hydrogen. And this one can also form a hydrogen bond with a hydrogen. Whereas with the ammonia molecule, it can only form 1 because it only has 1 lone pair. So it'd only have 1 going off in this direction. With a hydrogen, that would be 180 degrees. And these would all be 180 degrees. And that's why it only forms 1 because it has 1 lone pair compared to water, which has 2 lone pairs. So it can form 2 bonds with hydrogens. So before we start on number 2, feel free to pause on the video and try it yourself first. So ammonia is very soluble in water. State the strongest type of intermolecular force between one molecule of ammonia and one molecule of water. Draw a diagram to show how one molecule of ammonia is attracted to one molecule of water, including partial charges and all lone pairs. And phosphine has a structure similar to ammonia in terms of intermolecular forces, suggests the main reason why phosphine is almost insoluble in water. So first we're going to draw out the 2 molecules we have. So we have an ammonia, and that's NH3. So it'll look like this. With the 2 lone pairs. And then we have 1 molecule of water. So the water looks like this. And now we have a look at the intermolecular forces. So the 3 intermolecular forces are either van der Waals, dipole-dipole, or hydrogen bonding. And so, do we have van der Waals forces? Yes, we do, because they are present between all molecules. So we have van der Waals. Do we have permanent dipole-dipole? Yes, we do, because if we bond either the hydrogens with the nitrogen or the oxygens with the nitrogen, one of them will always be partially positive and the other one will be partially negative. So if we bonded a hydrogen to a nitrogen, there would be a permanent dipole-dipole, because nitrogen is a lot more electronegative than hydrogen. So we'd also have that. But do we have hydrogen bonding? And now we think about hydrogen bonding, and we know that it occurs when hydrogen bonds with a very, very electronegative atom. So basically, it's a very special case of permanent dipole-dipole attraction. And it only forms between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. So because we have a nitrogen here and hydrogens on the water, that means that we do get hydrogen bonding, because if we bond a hydrogen to the nitrogen, that will form a hydrogen bond because of how big the gap in electronegativity is, because nitrogen is so much more electronegative. So the strongest type of intermolecular force between one molecule of ammonia and 1 molecule of water would be hydrogen bonding. So for B, draw a diagram to show how 1 molecule of ammonia is attracted to a molecule of water. So if I draw out the water first, it looks like this, with the 2 lone pairs on the oxygen. So the oxygen is much more electronegative, so we give that the delta negative charge, and the 2 hydrogens have delta positive charges. And then we have the ammonia, which has 1 lone pair on the nitrogen. Then we have hydrogen bonding between the oxygen and the hydrogen, because the oxygen is much more electronegative than the hydrogen, because the nitrogen would have the partially negative charge, whilst the hydrogens would have the partially positive charges. And this would be 180 degrees. So this is how 1 molecule of water would be attracted to 1 molecule of ammonia. So that's for B. So for C, phosphine has a structure similar to ammonia in terms of intermolecular forces, suggests the main reason why phosphine is almost insoluble in water. So with ammonia, the lone pair on the nitrogen can form hydrogen bonds with the hydrogen of water. And so hydrogen bonds form, which makes it soluble. But when we have phosphine, so we have a lone pair on the phosphorus, and then the 3 hydrogens. So this would be the partially negative. These would be the partially positives. Because the lone pair is on the phosphorus, this doesn't hydrogen bond with any of the water molecule, so that's why it's insoluble.